So we kosher? It's in Warren, yep. 13 in, between 12 and a half and 13 in Shaner. Could be Burke, could be Tankenow, could actually be one of the other pulmonary physicians in the office. You guys will Dr. Tankenow is kind of on the quiet side. Dr. Burke is young, energetic, he's at St. John Macomb, you are correct. So you probably would have you may come in contact with him if you rotate through that facility. But a very dynamic, energetic guy. Some of the dates, there are 2 people going the same dates because there's 2 docs who can take the students with them. Okay. Be prepared to, answer questions as well as ask questions. This is a learning experience. So, questions on that? Yes, Ms. Emily Brown. I've already notified the clinical sites and sent them that thing, so it should be all set. If there's any issues, we'll find out. If you're assigned for, let's say, a Friday or a day that you normally wouldn't be in clinical, we'll just make arrangements for you to, you can make arrangements with your clinical instructor to choose another day to take off, in essence. So, or not. It's up to you. When I was a student, I couldn't wait to go to clinical and didn't want to miss any days. But then I'm not normal. But you know this. Okay. We're going to talk about errors in measurement and analysis, or sampling and analysis. We're going to talk about, pulse oximetry, you know that one, that's pretty easy. Talk about effects of temperature. And we'll talk about some other stuff out of Chapter 5. Did anybody read Chapter 5 yet? Brian, okay. Chapter 5 is kind of a hard chapter to read. I do like Malley as a text. I think he's a good writer, and it's probably, I think I may have said this before, but I'll say it again. It is probably the best referenced book I have seen. As far as everything he says, he gives citations that are in the back that you can go and quote. But 5 is a little bit of a hard read, and I'll try to muddle through it as best I can, and I'll tell you what you definitely need to know for the exam, because I'll be nice, and it won't happen often. So take advantage of it when you see it coming. Okay, so this is some of the stuff we're going to talk about. But how about a video?
Lips, $3,000. New chest, $8,000.
Don't tell him. I never forget a face. Don't help me here.
It's amazing the changes you can make for a few $1,000s.
Tom? Bob Johnson? Hi, Tom.
Imagine what Holiday Inns will look like when we spend $1 billion. Holiday Inn, on the way.
Yeah. Just a wee bit risque. Where's my, there it is. That's good, Will, because we're going to be taking attendance from this today, so. Since you weren't here last time. And poor Ryan's screwed. Well, you better know it. Oh, one day? The day before the exam? Good. I don't either. What was the line I gave to Emily earlier? Even a broken clock is right twice a day. All right, just reviewing back. John Dalton, Total pressure of a mixture of gas is equal to the sum of the individual partial pressures of each constituent gas. So if a gas comprises 25% of the total, it's going to exert 25% of the total pressure. And it has to do with the effect of changes in barometric pressure. So if we know the fractional concentration of any gas, we should be able to calculate the partial pressure of that gas. And this is kind of the way that we do the alveolar air equation. At various temperatures, remember that the pH2O will change. It's not always 47. That's assuming that you have a 37 degrees temperature, Celsius temperature. If the temperature is something other than that, you're going to have a different water vapor pressure present. Robert Boyle's law talked about pressure and temperature varying when volume has remained constant. Volume goes up, pressure goes down. To create a higher volume, you create a negative pressure. Think of a vacuum. Think of putting your finger over the end of a syringe, increasing the volume of that syringe, you now have created a vacuum within there. Chuck, Charlie watches TV, right? Temperature and volume vary inversely. As a temperature gets warmer, the gas expands and the pressure goes up. There's more collisions that are present. If I have a balloon that's normal size inside the house and it's in the middle of winter and I walk outside, that balloon will shrink. It will get smaller. And then finally, Gay-Lussac. He does kind of look like Gay-Lussac, doesn't he? It's from the movie Bone Collector. He was the evil person. His name's Leland Orser. But this relates to temperature and pressure if volume is maintained constant. A couple other folks, Henry's law. Henry's law talks about the dissolving of a gas inside of a liquid. Henry is into, Graham is through. And basically says it's dependent upon the temperature that is present as well as a solubility coefficient. And we know that CO2 is far more soluble than O2. This is one of the reasons your PCO2 changes at a greater rate than our oxygen level does. Okay? When you diffuse across the alveolar capillary membrane, we diffuse roughly about 40 to 60 torr of O2 change. We only diffuse a small amount of 5 to 6 torr change of PCO2. Because CO2 is far more diffusible. And Graham has to do with the rate of diffusion is inversely proportional to the square root of gram molecular weight. What the? So bigger items are going to diffuse more slowly. However, because it's taking a square root of it, it's not as appreciable. So even though CO2 is heavier than O2, it doesn't have as profound of an effect as it does the solubility. So Henry's and Grahams go together to affect diffusion of a gas through a liquid, meaning the blood. Some expressions. What we have inside of our body is BTPS. What we measure in the atmosphere is ATPS. And there is a standard temperature and pressure dry that is used for certain calculations. One of the features that occurs, for instance, if you feel on the 840, the filter that is, the expiratory filter that is there, if you touch it, it's warm. It's warm because it warms the exhaled gas back to 37 degrees so it can do a true BTPS conversion. Rather than having to rely on measuring the temperature of the gas and doing an ATPS to BTPS conversion, it warms the gas back up. So it knows that the volume that the patient is exhaling is corrected to the patient's pressure. When you measure blood gases, the blood you inject into the machine is warmed to 37 degrees. There's usually either a water bath that the electrodes are sitting in or an air chamber that's warmed to 37 degrees that the electrodes are sitting in, but the measurement is done at body temperature. Got it? Sure, Rick, whatever the hell you say. 5 errors that you need to know. 5 things that I can give you a description on of something that screws up. Okay? Air in the sample, venous blood contaminating my arterial sample, anticoagulant use, metabolic activity, and temperature disparities between the patient and the machine. So let's talk about them. Air, we know, in the blood sample is going to affect a couple of parameters. It's going to affect the PaO2 primarily. It also will affect the PaCO2 and therefore the pH, because the PaCO2 of room air is equal to almost 0. Yeah, it's like 0.4 or 0.03 or something like that. It's 0.4. But it's very, very small. This also makes a difference related to time. So if I have an air bubble in the syringe, given longer periods of time, it's going to have more of an effect. That's why we rapidly or as quickly as possible remove any air bubbles that you see. It's also dependent upon the size of the bubble to some extent, because a bigger bubble is going to be less of a problem than a bunch of smaller bubbles, because the surface area is less with a bigger bubble. Smaller bubbles have more surface area, more ease of diffusion of oxygen into the sample. Okay? We don't typically talk about air contamination during measurement, except maybe if we're drawing off an art line and one of the connections are loose and we get some air into the syringe at that point. Okay, whose gas law is this related to? Just Dalton's law. You're looking for longer time, lower temperature, increased agitation is going to have bigger volume present. Let me go back here and say, so which way does the PCO2 move? It's going to go down. An air bubble in your sample, because the air bubble has a PCO2 of roughly 0, it's going to pull your measured value closer to 0. So it's going to go down. How is it going to affect pH then? You're going to have an increase in pH. As CO2 goes down, pH goes up. What about PO2? Maybe. It's going to go towards 150. Let's use 150 since that's theoretically the partial pressure of an air bubble. The PO2 of an air bubble is about 150, 160 depending upon the barometric pressure. It's going to move towards that value. So if my real arterial value is a PO2 of 50, it's going to make that value higher. If my real PO2 is 250, it's going to make that value lower. So it's going to go towards 150. Make sense? Okay. Venous sampling. Contaminating my sample with a small amount of venous. Sometimes you'll see this in patients that are hypotensive. They may have a vein that's running directly over the artery. So as you puncture through the vein, you get a little bit of venous blood in there, and then you collect your arterial sample. It happens a lot with femoral veins because they're hard to find, and you often will get a small amount of venous blood added in. And the rough rule is a 10th part contamination leads to a 25% error. So it doesn't take much to get a pretty profound error in your bloodstream. So in other words, a half a milliliter of venous blood with a PO2 of 31 mixed with 4.5 milliliters of arterial blood of 86, you'll get a sample of about 56. So it doesn't take much venous blood, and that really is dependent too on what the PVO2 is and the PaO2 that we're dealing with is. But bottom line is, whenever your clinical results don't match what the blood gas analyzer is spitting out, you at least think about this as being a possible cause of a reduction in PO2 from what you would expect it to see. Make sense? A little bit of venous blood can profoundly affect your arterial PO2 value that you're measuring. Anticoagulants, I say they're a necessary evil. You can't have blood clotting, especially inside your blood gas machine. They will not be happy with you. But it really depends upon the type, concentration, and volume of anticoagulant. The preferred, as we said last time, is lithium heparin, although sodium heparin is still used, especially if you're using or non-standardized kits. If you're just using a regular 3C syringe off the shelf, you're going to heparinize it with some sodium heparin. And what you can end up having is obviously an increase in sodium because it's sodium heparin. You also can affect the PCO2 level, leads to reduction in PCO2. Also can alter some other electrolytes. And usually that occurs when you're using a concentration of sodium that's higher than 1,000 units per ml that is recommended. Okay? And again, because samples from a neonate off of a UAC is you're drawing such a small amount of blood off, any heparin that's excessive in that is going to drastically affect it because you don't have a lot of blood that you're drawing. Adults, you can get by with 2 cc's of blood. It's going to have less effect than my neonatal sample. Metabolic effects. Okay, and each of these are taken independently. Okay, so each will cause an alteration in blood gases, and you should have an idea what that alteration is. When metabolism, when the blood is sampled, that blood is containing cells that are still metabolizing. Okay, oxygen is being consumed from the blood, and CO2 is being produced and dumped into the blood. So depending upon the temperature of the sample, obviously a patient who's colder is going to have less metabolic activity, so it's not going to be as profound, but you will see a reduction in pH, an increase in PCO2, and a huge decrease in PO2. Okay? So we're basically talking somewhere on the order of 0.05 pH units per hour, 5 torr per hour, 20 torr per hour. I don't want you don't have to memorize those values, but just recognize that you're going to see a bigger change in PO2 drop than you are in CO2 climbing. Okay? Icing the sample slows this down, but it does still have that problem. That's why our solution is to analyze quickly. Shouldn't be sitting on a shelf or sitting on the table waiting for somebody to analyze it. There is also a special type of reduction in PO2 that you'll see, something called leukocyte larceny, where patients who have extremely high leukocyte counts, the leukocytosis, and you're looking at somewhere of 20,000 per cubic millimeter, that can lead to a reduction in PO2 and reduction in saturation just simply because those cells are consuming them. Okay? And that has been reported in the literature. Metabolism. Make sense? All right. And this is, again, just talks about the ARC's clinical practice guideline, analyzing as quickly as possible. And if you're going to ice a glass syringe, it should be iced as an immersion. Finally, there's an effective temperature. According to Gay-Lussac's law, pressure and temperature have a direct relationship with each other. Raise the temperature, raise the metabolic activity, raise the partial pressure that there is. Now, this is really talking about when there's a difference between what the patient's blood temperature is and what the analyzer is analyzing at. Okay? So if we have a patient who has a body temperature of 39, there's an argument to be made that we should be analyzing that blood at 39, not at 37. Others say, okay, but what's the normal for a patient who's at 39? Is it still the same as it was at 37? So you'll see controversies within the hospital. Some people always will temp correct. Some people will never temp correct. I don't have a good answer as to which is right because there isn't one. But any rise in temperature is going to cause a rise in PO2. And there's a mechanism by which you can temp correct a sample. Okay? And there's algorithms within the machine that you tell the machine this patient has a temp of 39, and instead of their... Well, here. What do you think would happen to my PO2? What's going to happen to my PO2? It's going to go up. What's going to happen to my CO2? It'll go up also. It's a gas, right? higher gas, what does Gay-Lussac's law say? Higher temperature, higher partial pressure. What's going to happen to pH then? Bicarb shouldn't be affected. Okay. So this is a situation where, you know, my PO2 is low. I want to make it look better. What's the patient's temperature? No, I'm just kidding. But you may, especially in extreme cases of temperature, most institutions will at least want to know what they are at that temperature. So, has that come up at all yet? You guys have worked in a blood gas lab? Or anything about that? Yeah? Okay. Okay. Now, this last part here is Chapter 5. And this gets a little bit confusing, like the rest was not. But it's talking about whether or not what measurements we have reflect reality. You know, we're assuming that this blood gas is correct. There's some errors we just talked about, 5 different errors that can affect whether or not they're correct. But assuming that those are okay, does the number I have make sense? Well, first of all, does the pH correlate with the CO2 and bicarb? If I said I have my pH of 732, bicarb or PCO2 of 23, and a bicarb of 31, that don't make sense. How can you have an acidotic pH with a PCO2 that's going to cause an alkalosis and a bicarb that's going to cause an alkalosis? Now, again, this kind of is not as relevant today where everything is computerized and the machines are hooked up directly to the lab system. This might be something where somebody was on the phone talking to the lab, got the message over the phone and just wrote down the numbers wrong. Okay? Instead of bicarb of 31, the bicarb is really 13. They just transpose numbers. Does the degree of pH change match the CO2 or bicarb change? I have a pH of 7.6, PCO2 of 30, bicarb of 23. For a 10-torr drop in PCO2, you have a 0.2 change in pH? Nah, that don't follow. 10-torr change in pH should yield a 0.08 change in pH. Do you agree with me?
I always agree.
No, thank you, Jerome. Jacqueline?
Can you say it one more time?
Sure. If I have a 10-torr drop in PCO2, I would expect my pH to rise by 0.08. That table I gave you the first day, if you take a look at it, that's what it's going to say. So to jump to 0.2, something smells funny. And it could be that my pH analyzer is out of calibration and needs to be addressed. There are 4 different methods that you can use to evaluate this, and I will not ask you any questions on these, but I want you to think about them, okay? I'm not going to say, okay, based upon the rule of 8s, what would you predict the pH should be? That's mean. I'll leave that to Mary. First of all, we have to know that there's a certain alteration in PCO2 and pH, or when the CO2 changes, there's a mathematical change in the pH that we end up having. And if you take a look at that chart that I gave you the first day, it says an acute decrease in PCO2 by 10 yields an increase in pH by 0.08. An acute change in PCO2 by 10 going up yields a drop in pH by 0.08. Okay? And we're going from a normal of 40. So if I go from 40 to 50, I'm going to have a pH rise of 0.08. Excuse me. If I have a rise in CO2 from 40 to 50, I'm going to have a drop in pH from 7.4 to 7.32. Mathematically, we can figure this out. Okay? Where does it come from? It comes from the Henderson-Hasselbalch equation. Oh, dread, oh, dread, oh, dread. Because in an acute, you don't have a change in bicarbonate. Okay?
The numbers are a little different in yours.
Yeah, it's 0.08. Yeah. If you look at, thank you for bringing it up, John. Malley has some different numbers than the ones that I use. I like Oak's mechanisms better. So that chart that I gave you, that's not the one that's in the, that one, has the values that we'll be using. And I will give you that on any test that it would be pertinent on. So in this case, if I had that expression there, that 30 PCO2 should yield a 7.48. 7.60 is the actual pH. Something's wrong, somewhere around along the line. There's also what is known as a rule of eighths, and this has to do with the fact that if I know the pH and the PCO2, pH is a nonlinear relationship. It's a logarithmic relationship. It's the log of the pK plus bicarb over PCO2. And there's basically factors that can be used to predict what the bicarbonate is. I don't know that anybody really uses this, but if I have a PCO2 of 30 and my pH is 7.6, which means I use a factor of 8.8, 30 times 8 is 240, divided by 8 is a bicarb of 30, not a bicarb of whatever we said, 23 that was on the blood gas. Okay? It's called the rule of eighths. There I've said it. Now you can ignore it. There's a Henderson-Hasselbalch that, although it's logarithmic, in a certain portion it gets pretty linear. But you can use this if I measure the nanoequivalents of hydrogen ions. I can use it to predict. Again, you're never going to use this, but there is a way to use the Henderson-Hasselbalch to predict pHs. I actually have created a spreadsheet that I can plug in a PCO2 and a bicarbonate, and it'll tell me what the pH is. Unless you got a log function on your calculator, you're never going to be able to do it. But if you ever get a weird blood gas, send me an email, and I'll let you know if it's possible. This is something, and we'll come back and play with this another day. But if you look at this, this is an excellent little handy tool to have. And what I know some students have done is they've actually shrunk this down, put it on the back of their badge, so that they could look at it. And, those are geeks. Huh? Sure you will. Here's. Oh, well, yeah. Got to blow it up real big. If I have my pH of 7.6, I have my PCO2 of 30, I come up, and you see it's not in one of these confidence bands. If I was, let's say, 7.5 and 50, I could say it's a metabolic acidemia. I'm sorry, a metabolic alkalemia. But it's kind of an interesting little tool to have, and we'll pardon me? Yeah, there's a picture of it in Malley. I think I might have actually have it on my 2350 site. But at any rate, it's there. You can laminate it. Does the values, yes? Yeah, it's because it doesn't fit the normal pattern. Something's amiss. And what we'll find eventually is that may be because there's multiple things going on. In other words, there's more than one disorder present. It's not our simple, easy to answer arterial blood gas analysis. It's based upon, I believe, a Seagard-Anderson nomogram. But it's like chapter 20 or chapter 18 in your text goes through a bunch of stuff. But we'll talk about it later. Okay? So we'll come back and visit it. Does your laboratory value make sense with everything else, with other laboratory values or other measurements? You know that value that you see on an electrolyte panel, sodium, chloride, potassium, CO2, right? Total CO2. You guys have looked at this before? Nod your head and lie to me. Thank you very much. That total CO2 is made up of the bicarbonate that you have along with the PaCO2 times 0.03, because this, in essence, is CO2. So if I look at my electrolyte panel and I see that my total CO2 is 18, and I look at my arterial blood gas and I see my bicarb is 24, it ain't possible. It's goofy. In fact, I used to work with a pulmonologist who hated to get blood gases on his patients. He thought we were causing far too much nerve damage. I don't know how the hell you manage a ventilator without a blood gas, but he used to do it. He used to look at the electrolyte panel and just watch the total CO2. It's like, I'm not getting you, guy, but it's your malpractice, not mine. Again, does the patient and the lab data make sense? If I have a patient who I measured their PCO2 as 65, they're not a chronic lunger, and they're talking to me and everything looks fine, that value doesn't make sense. Is there a correlation between the PaO2 and the FiO2? Again, this is where we end up seeing lab errors occurring, and you will see lab errors on tests from me. Thank you very much. Where they're drawn on room air, and the sum of the PO2 and the pH, sum of the PCO2 and the PO2 is greater than 150, roughly. And I usually make it really out of whack. Okay. Now, can that occur if my FiO2 is other than 21? Sure. Roughly, if you take the FiO2 times 5, you can get a ballpark of what kind of PO2 you would expect to see. Okay. And then finally, does it correlate with your pulse oximetry reading? If I have a PO2 of 60 and my saturation says 100%, think about it. Okay, so let's take a look at an example. And this is kind of giving you an indication of why the bicarbonate level may not always be true to you. Maybe telling you a lie. Blood gas comes on a patient that you see. 716, 80 PCO2, 80 PO2, bicarbonate 28. They obviously have to be on some kind of oxygen level. Otherwise, we would suspect a lab error, right? So I'm telling you this patient's on 100%. Do you guys get where I said that it has to be on some oxygen? Okay. Yeah, because PO2 and PCO2, I just said, can't be higher than 100, 140, 150. Here it's 160. So they have to be on some oxygenation. Oh, and here's some more data. Now, a couple of things that should pop out at you. First of all, how would you classify this? Partially compensated respiratory acidosis. Everybody agree? Okay, with corrected hypoxemia. So without the, if he's on 100%, the PO2 of 80 is corrected to normal, but that's not how it should be, right? What about that base excess? Too low. If I had a bicarb of 28, you would expect that to be above 0. Not below 0. And then what the hell is this other crap? STD bicarbonate, BE-ECF, T40 STD bicarbonate. Let's take a look at what they are. So if I look at this using those various methods, you can do the math because I don't feel like it, but that the 4 different methods we talked about predicts varying levels of bicarbonate. Something is wrong with that metabolic measurement. If I use the indirect metabolic measurement, going back a few pages, it predicts it as 24, not my 28. Rules of Eights predicts it as 22.5. Modified Henderson-Hasselbalch gets close, 27.6, but still not 28. So who's right? Well, this has to do with a unique situation that you will see whenever you have an acute respiratory acidosis or an acute respiratory alkalosis. If you have somebody who comes in who's in cardiac arrest and has a rise in their PCO2, you will see an alteration in PCO2, in bicarbonate levels, but it's not real. If you take a look at that chart, it says a 10 torr rise in PCO2 will yield a 1 milliequivalent change in plasma bicarbonate. So in this instance, I have a 40 torr change, so I'm going to have a 4 milliequivalent change in bicarbonate. It's not real. The kidneys haven't started holding back bicarb in that short amount of time. So why is this elevated? It's called the hydrolysis effect. And what happens is some of that CO2 that's inside the bloodstream moves into the cell, gets converted to bicarbonate, diffuses back out again. It's not because the kidneys are doing their job and compensating. It's just an artifact that exists because of the elevated PCO2 level. Okay? And that's really what ended up happening in our example. Just for explanation purposes, there are some other metabolic indices, and most blood gas analyzers turn these off. If you go and you look at the configuration, these are not checked, but they can measure them. They can express them. It just confuses the shit out of people. Last thing you want a doc to do is go, what the hell is STD bicarb? It's like, you don't want to know. But it's basically the bicarbonate concentration if I assume a PCO2 that's normal. Okay? And in our example here, it's not normal. Okay? There's also the T40 Standard Bicarbonate, and that assumes that the bicarbonate, that there's no metabolic activity going on. And then finally, I just want to go through the explanation of base excess, since we didn't do it up to this point in time, and you probably have seen them on an arterial blood gas, but it should track the same direction bicarbonate does. If it doesn't, then there's something else going on. And that hydrolysis effect is one instance of where it happens. Multiple buffering systems within our body. Okay? They occur almost immediately when a change in pH is happening, but they're quickly overwhelmed. The bicarbonate buffering system is the one that we have been talking about the most, but there's a phosphate buffering system. There's a the hemoglobin can act as a buffer. If you remember back when we went through that whole 6 ways CO2 is transferred, one of them was that CO2 comes into the erythrocyte as O2 leaves. It is also then neutralized. The excess hydrogen ions that are created within the presence of carbonic anhydrase, it goes from CO2 and water to bicarbonate and hydrogen ions. Those hydrogen ions are buffered by the hemoglobin. We talk about all the buffers that are present as buffer base, BB. When we compare the normal buffer base to the observed buffer base, we're basically calculating a concept called base excess or base deficit. Do we have more base than we need for a given pH? Okay. I said it wrong. This is derived by the Sigurd-Andersen, not the other one, nomogram. But in the presence of hypercarbia, you may get a low value there. It's telling us that we're short on base, even though we're typically not. And then there's the base excess of extracellular fluid, also known as the standard base excess. And this is probably the best way to look at how much buffering is present. So going back to our example here, this value is 0, this value is 24, both of them telling it that there's no metabolic activity going on. All of this change in bicarbonate is secondary to the CO2 moving into the cell, creating bicarbonate. The bicarbonate goes back out and the chloride shift. So, blood gas, 25-year-old female arrives in the emergency room in a coma. Bitch. 716 pH, PCO2 of 80, PO2 of 52, bicarb 28. Again, what should go in your mind, if I look at this blood gas, I would classify it as a partially compensated respiratory acidosis. But is it? Well, we can take a look. Does this base excess of -4 does not jive with this bicarbonate of 28. What we're seeing is basically that hydrolysis effect. By the way, what's the cause of the hypoxemia that is present? An elevated PCO2. If I normalize this, I normalize that. Change this by 40 torr, that comes back to normal. So it's simply a matter of hypoventilation being the cause of the hypoxemia. High bicarb, low base excess, yeah, that's true. Oh, and it's done. So this is an example of the hydrolysis effect that we talked about. and acute respiratory acidosis leading to that. Now, this is all in Chapter 5. If you really want to punish yourself, you can go ahead and read it. He goes through that whole concept of the hydrolysis effect. Sure. Hold on one sec. Let me do this.